Alright, so the topic today is five transistors. Okay, so yesterday we discussed about semiconductor diode. Semiconductor diode is made from two pieces of semiconductors. One is N-type semiconductor, another is P-type semiconductor. We stick them together. And when you stick them together, there are along the junction or the border, the boundary between the N-type and P-type. Now it will have emission layer. Okay, that emission layer. Okay, so because of this diffusion layer, the semiconductor diode can function as like a valve that can allow electric current to flow in one direction only. Okay. Now let's look at transistor. Okay, so this transistor is similar with the semiconductor diode. That means it is also made from doped semiconductor. Doped semiconductor, that means semiconductors that are doped with extra electron or doped with holes. That means doped with pentavalent, doped with trivalent. So that you can have extra electron, then we call it N-type. If doped with trivalent atoms, then there will be a hole. Okay? Alright. So all of this we already discussed yesterday. Okay? We discussed yesterday when we talked about semiconductor diode in topic 5.1. Okay. So transistor is different from semiconductor diode. Semiconductor diode is made from two layers of semiconductor, N-type, P-type. But for transistor, it is made from three layers of those semiconductor. So the combination is NPN or PNP. That means N-type semiconductor, P-type semiconductor, N-type semiconductor stick together, or P-type semiconductor, N-type semiconductor, P-type semiconductor stick together. Okay, so for example, like in this diagram, see, N-type semiconductor stick with the P-type semiconductor stick with the N-type semiconductor, or P-type stick with N-type stick with P-type. So it forms a transistor. So how does it work? How does it work? Okay, so later we'll go through this one, but we discuss the basic working principle of the transistor first. Okay, so let's say that this is transistor. Okay, so this is let's say this is NPN. Okay, so this is N-type. This is the P-type. So when these three types of semiconductor are stick together, what will happen is you will have division layer along the border, okay, along the junction. Okay, this one the boundary here. There will be division layer. Why? Because the N-type semiconductor will have extra electron. The P-type has hole, right? So the N-type, the extra electron in the N-type will migrate over, it will move over to the P-type and fill in the hole. So it will have division layer. That means the layer will have this lack of charge carrier. Okay, there is lack of charge. So you have division layer. So over this side also you will have division layer. Okay, you have this side also have electron over here, go over here, go. So on the n type here, this side there will be no extra electron, and over here then it will be. Okay, so you have the initial layer of the around the boundary or around the two junction of the semiconductor. Okay. Okay, so you see here what happened. So you see here you have electron. What is electron? Okay, so here also you have. Okay, so when you connect this to the power source, let's see what will happen. Okay, connect this power source. Okay, so let's say that it's happens. Okay, so this is positive, this is okay, so when we connect the power source, what will happen? So similar to what happened in the semiconductor diode, this negative terminal it will repel the electron. Okay, it will push the electron. So due to the negative terminal, it push the electron. So the electron will go over, uh, go nearer to the junction inside. So it will make the initial layer become narrow a little bit. Okay, narrow. But can the electron pass through the initial layer or not? Pass through the P type, pass through the N type? Why cannot? Because this side positive, it will attract the electron on this side. So that means the electron on this side move away from the junction. When move away from the junction, what happens? That means here, near the junction, uh, the electron move away, so that means no electron. No electron, that means the emission layer will become emission layer will become emission layer. So you see the electron from over here cannot pass through. Okay, it will not be able to pass through. It cannot pass through, then that means no current. Okay, current cannot flow. So if you connect a bulb here, okay, if you connect a bulb here, then this bulb will not be able to turn on. Current cannot flow. Okay, so now what if we turn this around? Same like in the semiconductor diode. In semiconductor diode, when we change the switch the positive and the negative terminal, and then the current can flow. Right? Okay, one side current when connect the forward bias connection, the current can flow. Connect in reverse bias, current. So let's see what will happen in transistor. Is transistor going in the same moment? Okay, again when connect like this, and one of these, we have initial layer. So let's join our source. Now, okay. So this side become positive, this side become negative. So let's see what will happen. Okay, so this positive will attract the electron away from the junction. So what happened? The diffusion layer on this side become bigger. Okay, the diffusion layer on this side become bigger. Okay, diffusion layer on this side become. Then this side, the negative, it will repel the electron, then push the electron. Push the electron. So the diffusion layer on this side become more. This side diffusion layer. However, if we connect about here, and the bulb light up, of course cannot. Because see, here still got diffusion layer, and the diffusion layer here become bigger. So that means the electron cannot pass through. Electron cannot pass through the transistor. So that means electric current cannot flow. Current cannot flow, then the bulb will not light up. Okay, bulb will not light up. Okay, now, so if cannot, if current cannot flow, so that means what is the transistor good for? What is the transistor for what? But current cannot flow. So here, one very special thing about the transistor is here. What we are going is we connect another power source. Okay, so this can be a stronger, this can be a strong power source. Okay, strong power source. Okay. And then here, over here, we connect, even though we connect to a strong power source, still cannot pass through uh, the electron still cannot pass through. Because this, if you connect to a stronger power source, what will happen is this side, the diffusion layer will become narrow. It's more narrow, but this side over here, the diffusion layer will become bigger. Because this becomes stronger positive. This becomes stronger positive, so you can put more electron away from the junction. Pull more electron away, so this diffusion layer becomes bigger. So that means at the end, the electron over here still cannot pass through. Okay, no matter how strong this side push the push, still cannot pass through. Because this diffusion layer becomes bigger, become more bigger. Okay, stronger also. Okay, get that. So that means current still becomes bigger. So how is it that see we connect here another power source. Okay, connect here the power source that is small power source. Okay, connect to the P type. Okay, so if you still remember, previously we say that when the N-type comes out with initially, and across the junction there will be junction voltage. Okay, there is going to be junction voltage. So let's say that this junction voltage is 0.7 volt in this junction. So when you connect this power source to this small power source, let's say it's 0.5 volt. So what will happen is, see, this small power source is forward bias. It is forward bias to these two layers of the semiconductor. So this is P type, but this center here, this is P type, this is N type. Okay? This is P type. This is N type. This is N type. So you see this positive connected P type, negative connected N type. So that is this power source is forward bias. Okay, forward bias to these two layers of the semiconductor. So what happens is, because here 0.5 volt, so here negative it will push the electron. Okay, push the electron. So that means here the emission layer becomes important. Okay, emission layer becomes important. Over here positive, it will push the hole for extract the electron. So that means the diffusion layer on this side also come on. Okay, so the diffusion layer on this side also come on. But still got diffusion layer. Why still got diffusion layer? Because the power source, this one, the voltage of the power source is lower than the junction voltage. So still cannot completely overcome the diffusion layer. However, if this power source is increased to, let's say, 1 volt. 1 volt is higher than the 0.7 volt junction voltage. So what happens is, this division will disappear. Okay, this division will disappear. Okay, because this positive is strong enough, now the whole flow over here, and this negative is strong enough to push the electron to pass through the junction. Okay, electron can pass through the junction here. The electron can pass through the junction, so the division will disappear, and then electron can flow. The electron can flow. So when electron can flow, that means you will have current. Okay, you will have current. Okay, current. Okay, current can flow from this layer at the center here, this side. Okay, current. See the current. So when the current can flow, what happens? This center layer, this layer and the center here, there will be a lot of electrons able to move around. So what happens when the p-type layer here is have a lot of electrons? That means here the negative is strong, and then it will be able to push the electron out from the hole over this side. So that means it will be able to make the diffusion layer here up and the bottom. Okay, it will be able to make the diffusion layer here up and the bottom. Okay, the diffusion layer here up. And then because of the positive here, this is strong positive, right? So that means this strong positive will be able to pull, because this side becomes narrow already. So that means it will be able to pull some of the electron from this side, pass some of the electron will be able to be pulled and pass through this junction. So that means when over here, the diffusion layer here also for electron can pass through. So that means this diffusion layer also become, okay, also become, but still got diffusion layer, we still consider it as the diffusion layer is still there, just that the diffusion layer become more, okay. So if we increase the voltage here, if this voltage here 1 volt, we make it bigger, let's say we increase to 2 volt, that means that more electron can pass through over here. And that means the center layer here, this p-type layer will have even more electron, that means even more charge. Even more electron, even more charge carrier, so that means more electron can be affected by positive here. That is more electron can pass through. Okay, more electron can pass through. If more electron can pass through, then this layer here will be even more narrow. Okay, so you see the bigger the voltage here, the bigger the voltage and this between the p-type here, then the greater the amount of electron that can pass through. That means the bigger the current that can flow. Okay, flow through the transistor. So you see at this time when the electrons start be able to pass through the transistor, so that means what? That means you will have current. Okay, that means electric current can pass through the transistor. Okay, so electron can flow and pass through, that means no current. Okay, no current, so that means this bulb turn on. Okay, this bulb will be able to light up. Okay, let's see. So you see, this transistor can become like a switch where this small power source can control whether this big power source current flow. When this one is higher than the junction voltage here bigger than the junction voltage, we say that the transistor is turned on. Because when it's higher, then that means the electron can pass through the transistor. The electron can pass through the transistor, so that means the current over here can pass through the current. Okay, like that. Okay, here current can flow. The bigger the voltage here, the bigger the current. Because the bigger the voltage, the greater the amount of charge carrier that can pass through the transistor. More electrons can pass through the transistor, so bigger current that can pass through the transistor. So that means when you increase the voltage here, you'll be able to see that the bulb becomes brighter because the current increases. Okay, so the current will become higher. And this voltage will become higher and the current will become higher. Okay, So another way of saying is that this transistor is like a variable resistor. That means it's like a resistor when the resistance. Because you see, when this voltage here is lower than the junction voltage, totally no current can flow. So it says that the transistor is turned off. So how is it that transistor is turned off and no current can pass through? Because the resistance of the transistor is very high. The resistance of the transistor is very high due to the voltage here. But when we increase this voltage here and become higher than the junction voltage, then the transistor is turned on. Okay, we say the transistor is turned on and current can flow. Why current can flow? Because the resistance of the transistor increased. Okay, that's the other when charge can pass through. So more charge carrier will also the resistance go down. Okay, resistance of the transistor increase. And the greater the voltage here, okay, this voltage, the greater the voltage, the greater the amount of charge area that it pass through. So the greater the current. Okay, so the greater the current, so that means the lower the resistance. Okay, that means the resistance of the transistor go down. So you see, this transistor can function as a switch where the small current or small voltage can control the big voltage. Okay, this small voltage turn on the transistor, then allow the big voltage of the current of big voltage to flow. So small current control big current. Okay, and also it can make the big current become bigger because when this voltage increase, resistance go down, and this current can become higher. Okay, the big current become higher. Okay, so this is the function of the transistor. The function as a switch or automatic switch. Later we will see how it functions as automatic switch. Okay, or it can function as an amplifier. That means it can make the current here over this side become higher. Okay, control the size of the current here. Okay, and then okay. So now that we already discussed how is it that the transistor works, okay, how is it that the transistor works? So now we want to discuss about the name of the part of the transistor. Okay, so you see here, this center part of the transistor, okay, this center part of this, okay, this part of the transistor, okay, or this terminal, okay, this terminal. Now this terminal, it controls whether the transistor is on or off, okay, whether the transistor can allow more charge to pass through or only a little bit of charge to pass through control the amount of charge. Okay, here, because this terminal it control whether the transistor is on or off, control how much current or the size of the current that pass through the transistor. So we call this terminal as base. Okay, and then you see this terminal here. Here it supplies the charge because the electron go inside here. Okay, here negative, put here positive, here negative, put here positive. So it supplies the charge carrier. Okay, it supplies the charge carrier. So or we say that it big charge carrier. So we call this terminal here over here, this side, this terminal, we see the charge area, see the charge area. So we call this the okay. So we have say the transistor have three terminals: the base, the emitter, and the collector. Okay, and then this circuit, okay, this circuit that connect between the base and the emitter. So this circuit here, this flow of current here, this circuit here, call this the this. Okay, or so the current that flow here, call it the base current. Okay, call it the base current. And then here, this circuit here, this bigger current, this circuit that allows the current to flow here over here. So this circuit, we call it the collector circuit. Okay, call it the collector circuit, and then the current here is positive of the current. Okay, of the current. Okay, so these are the names that they are involved here. Okay, and then you see the current here is the collector current right now. So the symbol that we use is I small c lah. And then here the current that flow here, this is the base current. So we use the symbol of I. Okay, base current. And here, this current here, the current that only flow through here, here to here, okay. Here, from here to here, this short part, here to here, okay. So this current here, okay, this current here is the emitter current. Okay, the emitter current. So you see here, because this base current flow here pass through this part, and the collector current, you see the collector current flow here, flow through here also. That means the emitter current is equal to the collector current plus the base current. Okay, the emitter current is equal to the collector current plus the base current. So that means if the collector current is 1 ampere, base current is 0.1 ampere, so the emitter current will be 1.1 ampere. Example. Okay? Okay, so these are the working principle and also the names of the parts of the okay. So you see here, this is for NPN transistor. Okay, NPN transistor. So for NPN transistor, the charge carrier here will be discussed. We are all talking about the flow of electron. So the charge carrier is charge carrier from NPN transistor is electron. Okay, next we want to talk about PNP transistor. Okay, although it's different, PNP, but actually the concept is still the same. The concept is the same. So let's look at PNP transistor. Okay, so here. Okay, like this. So this is P type, this is N type, this is P So same thing also, when join together, there will be diffusion layer. Okay, here the diffusion layer. Here also the diffusion layer. Okay. Layer, here also got diffusion. And then so all this is a PNP, so here we go. Okay, here also. So remember the ball represent positive charge. Okay, so when we connect to power source, okay, when we connect to power source, okay, this is positive, this is negative. So what happens? This positive it will repel the hole. Remember, the hole represent positive charge, so this positive represent repel the hole. Repel the hole, so the diffusion layer here become more negative. Okay, the diffusion layer here become more equal. And the opposite side, this part, negative, it will attract, it will pull away the hole. Okay, because the hole is positive, remember. So positive, negative, they attract each other. So the negative terminal here will attract the hole. So the hole will move away from the junction. So this diffusion layer becomes bigger. Okay, the diffusion layer becomes bigger. We can see the diffusion layer. So if like that, same like just now, if we connect the valve here, can light up or not? Cannot light up because the electron cannot pass through. Oh, sorry, the hole cannot pass through, so no current. Not okay. So how to turn on the transistor? Same like just now, we connect another power source here. Okay, connect to another power source here. Connect to this center layer. This power, if you want to turn on this power source, it must be forward bias connection to this layer. Okay, this one positive, then see positive, the P type. Negative is the N type. This center is the N type one. Okay, so it must be forward bias. When forward bias, so what happens is this one the positive, it will be able to repel, to push the positive pole. So the positive pole can move towards the junction. And then here, the negative will be able to attract the hole. So, attract the hole. So what happens is the hole will be able to pass through the diffusion layer because it is forward bias. Of course, this voltage, the voltage here, this voltage of this small power supply here, it must be higher than the junction voltage. Gate here also got junction voltage, so that's H0. So if this is on volt, then it will overcome the junction voltage. So it will be higher than the junction voltage, so it will overcome the junction voltage. So this diffusion layer will disappear. Okay, no more diffusion layer. Okay. So no more diffusion layer. So the hole can pass through. So the hole can pass through, the hole will be able to go. And remember, the hole represents positive charge, so that means the direction of the current is the same as direction of the flow of the hole. Okay, the direction of flow of hole is the same as the direction of the current. So here got current and flow. So say like just now MPN, when hole can flow, that means at the center here have a lot of hole. A lot of hole start to flow, so there will be a lot of hole at the center layer there. So when got a lot of hole at the center layer here, then you will be able to repel the hole that form the initial layer. So that means this initial layer, this side is become more narrow. Okay, become narrow, and then some of the hole can be attracted by the attracted by the negative terminal here. So some of the hole can pass through the depletion layer here. So then this depletion layer also become narrow because start to have charge carrier, all over on this side. So the depletion layer will also become narrow. Okay, narrow. So got current can flow, got positive charge carrier, which is the hole, can flow, then that means got current flow lah. Okay, got current flow. Okay, got current flow, so this bulb will light up lah. The bulb will light up. So that means now we say that the transistor is turned on. Okay, we say that the transistor is turned on. The resistance of the transistor is low. Okay, and the collector current can flow. Okay, so same thing also. See, here this center, this terminal control how much charge can pass through. Okay, control how much charge can pass through. Then it can control the size of the current here. So all this this emit the charge carrier. The charge carrier here is the hole. So it emits the hole come out here. So this is the here collector receive the charge carrier, receive the hole. So this is the collector. So same thing also. This is the base. So the current that flow here, this is the base current. This here, this is the base conductor. So here, this is collector. So this is collector current. And this is the base. So this is the collectors. Okay. So the charge carrier for PNP transistor is okay. Charge carrier for PNP transistor is the O. Okay. So this is the transistor. Here is how the transistor function. Turn on, turn off, increase the resistance, increase the resistance, just by manipulating the voltage here. This voltage higher than the junction voltage, you can turn on the resistor current flow. And when you further increase the voltage here, then you can increase the number of charge carrier that pass through. So that means you increase the current that pass through the transistors. You want to decrease the current, increase the voltage here. Okay, the voltage at the base circuit, and then the number of charge carrier that pass through will increase. So the current increase, the bulk will be. If you decrease the voltage here until less than the junction voltage, then the emission layer will appear again, and the resistance of the transistor will become very high. Charge carrier cannot pass through, so current cannot pass through, so bulb cannot light up, and we say that the transistor is off. Okay? Okay, so until here, anybody have any concern about transistor? Okay, so no question. Thank you very much. Thank you very much for responding. Okay. As always, your response is the motivation for me now. Okay. So you can put me on board. So I know that. All right. So now let's look at the let's just go through that. So, okay, so we have NPN transistor and PNP transistor, both also discussed already. So here, this one is the emitter, this is the base, this is the connector. So PNP, this side here is the emitter, this is the base, this is the connector. Okay, so let's look at the symbol of the transistor. So the way that we draw the symbol of the transistor is we draw a circle. How we draw the so we draw the circle, okay, and then we draw a line here, and so this one is the base, okay, this one, and then over here, join here, and then another line, join here. Okay, now the arrow of the arrow, it depends on whether this is NPN or PNP. See, this is NPN. So the current flow from where to where? The current flow from P and right, from positive to negative. P positive to negative. P, and that is base. The current flow from the base to the emitter. Okay? Current flow from the base to the emitter. The electron flow from the emitter to the base, but the current flow from base to emitter, because current and the electron is junction. So current flow from base to emitter. So we draw the arrow like this. So this represents NPN transistor. Okay, so the NPN transistor, the second arrow. So this arrow represents the direction of the current. So base is the conductor. Okay, and then for the PNP, the way that you draw the symbol is the same as your circle. One line here. So this is the base. Okay, and then same thing. See here, what is the direction of the current flow? Well, this is PNP. So the current flow from the P, from the positive to the negative here. From the positive layer to the negative layer. That means from the emitter to the base. So the arrow is the emitter, the base. So this is P and P. Current from the flow from emitter to the base. Okay. So So this is how we draw the electronic symbol for the NPN and the PNP transistor. Yeah. All right. Video. Okay. So what is the function of the terminal of the emitter? Supply charge carrier to collector. Collector receive charge carrier from emitter. This thin layer in the middle to control the flow of charge carrier from emitter to collector. So you see here in this diagram, it shows that that the base, this layer here at the center is thinner compared to this layer and this layer. The layer at the center is thinner. So in reality, that is true. In reality, this PNP, NPN, the center layer, the layer where you have the base, the middle, is thin. Okay, it's much more thinner compared to the layer compared to the other layer. The reason is so that when the charge carrier go to the center layer, so that when the charge carrier go to the center layer, it can easily fill up the center layer with a lot of charge carrier. Okay, that is why we want to make the center layer become thin, so that easily fill up with charge carrier. When fill up with charge carrier, then the charge carrier can be attracted and pass through the other side, pass through the layer. Okay, understand? So if this center layer is too thicker, then it's difficult to fill up with charge carrier. Yeah, so there's the middle layer or the center layer. It must be thinner. Okay, so let's go through here. Okay, when the switch is open, in this switch, okay, when the switch is open that means off. Bulb L1 does not light up as circuit is incomplete if the base current is 0. See here, this one is off. So that means not have potential difference. The potential difference or the voltage between the base and the emitter is base. So the voltage here is 0. So if the voltage here is 0, then that means the transistor is turned off. Okay, the transistor is turned off. Current cannot pass through. Okay, okay, so bulb L2 does not light up, although the collector circuit is complete because the transistor is not turned on. So if not turned on and the collector current is 0. So here, this bulb is not turned on. Even though you see this one is complete, but current cannot flow because the transistor is not turned on. When the switch is closed, this one on, bulb L1 is dim because RB has a high resistance. That means this one, okay, you see here, this circuit they connect a big resistor here. Okay, there's a big resistor here. RB has a high resistance and the base current is very small. Okay, so this base current is small. Actually this is done on purpose. Okay, they done on purpose fully. They on purpose put a big resistor here so that the base current is smaller. Okay, so bulb L2 light up very brightly because the collector current is large compared with the base current. So you see this bulb is dim, but this bulb is bright. Okay, so that means a small current control a big current. Okay, so this small current control a big current. So a big this one small current already turn on the transistor. When transistor turn on, then this collector current will flow. This turn on. Okay, this one is bright. Not this one, the bigger voltage, so the current. So this one is dim, not the current is small. Okay. So a small base current can produce a minimum base voltage. Turn on the collectors. So this voltage here, we also call it the base voltage. But this base voltage is the same as this here. Okay. This base voltage. Right? So the small base voltage on the collector circuit. Base current can control the flow of the collector current. This enables the transistor to act as a switch. So the resistance at the base circuit is large, limit the base current, so that the transistor will not become hot. Okay, like what I said just now, we purposely put a resistor here so that the current between that flow from, so that the current and the flow from the between the base and emitter is not very high, so that the current is so small current flow. Okay. All right. Continue. Okay, now we want to look at the application of the transistor, how to use the transistor. So first is transistor as a current amplifier. Okay, as a current amplifier. Alright, so let's look at this circuit. So here we have a transistor, here we have a transistor. So here we have a small power source, 1.5 volt. And here we have a bigger power source, 6 volt. Okay? Alright. So let's look at the procedure. It says record the reading of A1, that means here, emitter 1, as current as the base current, and this reading here, emitter 2, as the collector current. Okay. So you see here, first we record, okay, when this resistor is 2.2 kilo ohm. Okay, this is 2.2 kilo ohm. Okay, okay. And then after that, we place 2.2 kilo ohm resistor, that means this resistor, we place with 3.9, 4.7, 6.8, 8.2 kilo ohm. That means we slowly increase the resistance here, and then we see what happens to the reading here and the reading here. Okay, so of course, what is it that we can see is as the resistance increase, this base current will increase. So that means this is high, this is higher, and this one will be lower. Okay, lower. And then we will be able to see also that this collector current also here is higher. And then the collector current also becomes lower. So that means when the base current, when this current increase becomes smaller, this collector current also becomes smaller. Because when this base current is low, that means the amount of charge carrier that can pass through the transistor increase. Okay, the resistance of the transistor increase. So the collector current increase. So the reading of the potentiometer will increase. Okay, so in this sense, we can say that the transistor acts as a current amplifier. because if we do the opposite, then we increase this resistance. Then if this resistance increase, this current will increase, and this current will become higher also lah. So you can use the transistor to increase this current. Okay. So in this sense, we say that it is the current amplifier lah. Okay, current. Alright. Okay, so look at here. Okay, so here, this is how we want to calculate the amplification factor. Okay, amplification factor is we want to look at the ratio between the collector current and the base current. We know that the collector current is bigger than the base current, but bigger by how much? Okay, collector current bigger than the base current by how much? So we take the collector current divided by the base current, we get this number. So this is the amplification factor of the amplifier lah. Okay. Alright. So look at here. So this is the base current. You see this base current is very small, 0.5 milliampere. But when the base current is 0.5 milliampere, the collector current is 78 milliampere. So 78 divided by 0.5, you get 156. So that means the collector current is 156 times higher than the base current for this transistor. Yeah. So it's here when there is no base current, there is no collector current. When the base current increases, collector current also increases. So the gradient of the graph is an amplification factor of the transistor. A small increase in base current will cause a big change in the collector. Okay. So you see here, because the collector current is 156 times the base current, so this means that a change of 1 milliampere, the base current will cause a change of 156 milliampere in the collector. Okay. Okay. Before we continue, okay, I want to explain a little bit about the further application of the current and of the transistor current amplifier. I want to explain further. Okay, so then I discuss about next application. Yes. Okay. Okay. Okay, you see here. Look at the transistor circuit. So you see the transistor can only be turned on and there is a power source here, right? Okay. So then maybe you have one big power source here and then you have another small power source here. Okay, if you have power source, then you have however, by using the potential divider, okay, by using the concept of the potential divider, we can turn on the transistor transistor without the small power source. Okay, so you see it says here a transistor requires a potential difference between base emitter, which is more than the minimum voltage for the transistor to function. Turn on. In the potential divider, two resistors are connected in series with the power supply. So this is the input. And the same current flow through both resistors. The relationship between the voltage and the resistance can be right. Okay, so here we can turn on the transistor just with one power source. Okay, you see here this is positive. Okay, so you see, let's say that this is 10 volt. Let's say this is 10 volt. So when we connect the two resistors here in series, what happens is if this resistor is 9 volt, this is 1. If this is 9 volt, this is 1 volt. What will happen is the potential difference across the resistor. You see, these two resistors is connected in series and then connected to this power source. So that means from here to here, the voltage is 10 volt right now. Okay, here to here is 10 volt. Okay, so if this is 9 volt, this is 1 volt, so that means the voltage here will be 9 volt, and the voltage here will be 1 volt. So now, series, so 9 volt plus 1 volt equal to 10 volt. See now, okay, 9 volt plus 1 volt equal to 10 volt. So you see, this transistor is connected in this way. So that means the potential difference between this point and this point is 9 volt. So that means this bulb get 9 volt. Wow. Here, this point and this point is 1 volt. So that means this point and this point between the base and emitter, the potential difference of the voltage is 1 volt. So you see, the minimum voltage to turn on silicon transistor and active resistor is 2.7 volt. So that means this 1 volt is already higher than the minimum voltage, 2.7 volt right now. So that means this 1 volt here, and here, already higher than 2.7 volt. So that means we can turn on the transistor. So when the transistor turn on, then that means current can pass through the bulb, or it can pass through the transistor. See now, current can pass through the bulb, pass through the transistor. So that means the bulb will be able to light up. Okay, we can turn on the transistor and the bulb can light up. So you see, we can turn on it by using this two resistor. That with this arrangement, that call the potential divider, because we divide the potential divider. Okay, so for the potential divider, we can turn on the transistor even with one power source. Okay, you get the idea. Okay, all right. So the current flow in both resistors is equal to current in R2. That means this current and this current is the same. Okay, then the current is the same. Okay, so until here, any problem? Any question here? Okay. Anybody have any question? Okay, thank you very much. Thank you very much for the comment. Yeah, all right. So let's continue. Okay, now that we learned about the potential divider already, okay, let's look at transistor as an automatic switch. Okay, transistor as an automatic switch. Okay, or not lah. Okay, I think I discussed about how is it that we can apply the transistor as a current amplifier. Okay, further application. Because if you look at this, we cannot think of like any useful application. But why you want to small current? So whether it's current or small. Okay, what is the point? Okay, you can see the point there, right? Okay, because the actual application is not just like this. Okay, the actual application for the current amplifier, transistor as current amplifier is actually not just like this. Okay, okay. So look at this one, transistor as amplifier. Okay, this is the more useful application for the transistor as amplifier. Okay, I want to explain this just in case just in case question come out, right? And I will show this application. Okay, so you see so you look at this circle. So this circle, this is a transistor, and this is the power source here, and you can see that two resistor here. So these two resistors act as a potential divider. Okay, so these two resistors here act as potential So this is 40 kilo ohm, this is 10 kilo ohm. So for example, you see this the ratio is 4:1. So that means let's say that example if this is 5 volt, okay, if this is 5 volt, so that means here the voltage here is 4 volt, and here the voltage here is 1 volt. So this 1 volt is enough to turn on the transistor. So when the transistor is turned on, so that means current can go up, pass through the loudspeaker. Okay, current can go, pass through the loudspeaker. This is collected current. So you can hear like the sound coming from loudspeaker. Sound like that. Okay, not a bit like something like that. This sound coming from not the loudspeaker. Okay, now you see here. Okay, you see if we see if we draw a graph, of the current, or sorry, we draw a graph of voltage between the base and the okay, the graph of the voltage between the base and the so this. Okay, the voltage between base and the okay, so because this is direct current, okay, direct current, so that means you can see that the voltage is always the same. So this is 1 volt, okay, 1 volt, okay, right, constantly 1 volt voltage between the base meter. So because the voltage of the base meter is constant, always 1 volt, so that means the current that pass through the loudspeaker also always constant, always the same, doesn't change, okay, always the same, doesn't change. Okay, now you see over here, it is connected to this point and this point, you see. This point and this point is connected to the microphone. Okay, and see, I'm connected to the microphone. So what happens is when you talk into the microphone, and sound go into the microphone. What happens is the microphone will be able to convert the sound wave, the vibration from the sound into potential difference. Okay, into alternating current. Okay, you will be able to produce alternating current. If you can produce alternating current, that means you will be able to produce alternating EMF. That means the electromagnetic force that is produced by the microphone is alternating in two directions. So let's say that we draw a graph that shows the alternating EMF that is produced by the microphone. So the voltage of the microphone input amp. Okay. So the voltage that is produced is because it's sound, so the frequency and the amplitude of the voltage will depend on the sound. If the sound is loud, then the voltage will be higher. If the sound is soft, then the voltage will be smaller. If the sound is high pitch, then the frequency will be higher. If the sound is low pitch, then the frequency will be lower. Okay, but because the vibration is very small, so the EMF, the voltage that is produced by the microphone, is also very small. So, for example, this voltage is only like 0.1 volt here, 0.1 volt. So this is negative 0.1 volt. Okay, and here is 0.05 volt. For example, okay, now you see this voltage that is produced by the microphone is connected to this point and this point. And you see the voltage between base and emitter is also this point and this point right now. See. Okay, the voltage between base and emitter is here and here. The voltage that the microphone supply, is here and here. So what happened is the voltage from the microphone will add on to the voltage from the power source. That means this 1 volt. The voltage from the microphone will add on to this 1 volt. So that means the voltage of the base emitter, that means this one is voltage will add on to here. So, for example, 0 volt increase to until 0.1. So this one will increase until 0.1. Okay, for example, so that means this voltage of the base emitter will change. So this is 1.1 volt. Here is 0.9 volt. Okay, in 1 volt, 1.1 volt, because 0.1 volt can on to 1 volt, so 1.1 volt. So this negative 0.1 volt and on 1 volt, so it becomes 0.9 volt. So the voltage of the base emitter will change because of the influence of the voltage from the microphone. So when this happens, the resistance of the transistor will also change, right? When the voltage between the base emitter go up and down, up and down, up and down, so the resistance of the transistor also go up and down. So what happens is the collector current, this collector current also go up and down. The current that passes through the loudspeaker also becomes strong and weak, strong and weak, strong and weak. Follow the frequency of the sound that go into the microphone. So the frequency of the sound is the same as the frequency of the voltage produced by the microphone. And then that frequency will be the same as the frequency of the changes in the voltage of base emitter. So the resistance change up and down, also same frequency. So the collector current go up and down, strong and weak, also same frequency. So this will be able to make the loudspeakers diaphragm. So the loudspeaker will be able to vibrate with the same frequency as the sound that go into the microphone. So the loudspeaker, because it has a higher voltage, so the sound that is produced by the loudspeaker will be louder. Okay? Sound from the loudspeaker will be louder. Because the voltage is higher, so the current is collected current that flow through also higher. Okay? Get the idea? So this is the application of the current, the actual useful application for the current amplifier for the transistor. See or not? It can make the small sound become louder sound. Or in another words is it make a small or big signal. The information, the signal, the wave that is bigger, that is big, small and bigger from the microphone become a bigger and stronger signal, stronger and bigger. Can see or not? Okay, get the idea. So this is the actual application for the transistor as a current amplifier. And of course, the actual circuit in the amplifier, okay, is like the PA system. The PA system you have the amplifier. So of course, the actual circuit is not so simple, okay, because the actual circuit, the sound can become very very loud, right? Very loud. So how is it that they make it very very loud? Is this output this output here loudspeaker, it doesn't connect to loudspeaker, but it connects to another input. That means have another similar circuit connect to this output. That means this output go inside here, where the microphone go inside here, go through the transistor and then make it stronger again. Then output and then go through another circuit and stronger. So it can amplify the signal, amplify the sound many times. Okay, and of course there are also other more complicated electronic circuit that can make the sound clearer and also input a lot of different amplification to the sound, like put it effect and so on. Okay, so this is the application for transistor as current amplifier. Okay. Okay, if you got question, please ask. All right, so continue. Okay, continue. We want to look at the next application. Please. Transistor as an automatic switch. Okay, how is it that the transistor can function as an automatic switch? Okay, so we have a light dependent resistor with a light control switch. Okay, so let's look at this light dependent resistor. So this light dependent resistor, or in short form is called LDR. So if when you answer question, you don't need to write the whole word, you write light resistor, you can write LDR, the short form for the light dependent resistor. Okay, so LDR is a type of resistor. Its resistance changes with the intensity of light. The LDR resistance value is high when the light intensity is low and vice versa. Okay? In the dark, LDR resistance is very high. Based on the concept of potential divider, voltage across LDR will increase when the voltage of LDR value exceeds the minimum voltage across base and emitter, base current will flow and turn on the transistor. So this condition causes high collector current flow in the collector circuit and the bulb will light up. And under bright condition, the resistance of LDR is low, thus voltage of LDR will increase. When the value of LDR, voltage LDR is less than the voltage of the base transistor, then no base current flow to turn on the transistor. This situation causes collector current not to flow and the bulb does not light up. So the circuit is using auto and DC. Alright. So let's look at how it works in the circuit. Okay, you see here, the power supply here is 6 volt. And then you have potential divider that is made from this resistor, 10 kilo ohm resistor, and there is an LDR, light dependent resistor. So this light dependent resistor is actually a variable resistor. That means the resistance can change. Okay, how does it change? Is during daytime. Okay, LDR. During daytime, the resistance will be low. During nighttime, the resistance will be high. Okay, actually, this is very easy to remember. You see, this LDR is actually made from semiconductor also. And this LDR is also made from semiconductor. So one very special thing about semiconductor is when it is struck by light, when it is exposed to light, the electron will be able to absorb the energy from light, and the resistance of the semiconductor will increase. So you can see why is it that during daytime the resistance will increase, and then during nighttime the resistance will decrease. So the electron can absorb energy from light. So electron have more energy, electron easier to flow up, absorb energy from light, energy increase, so easier flow. Or you can say that number of free electrons increase up. Okay, we have more free electrons. So easier to flow, resistance decrease. Okay, so the resistance. So during daytime, the resistance of the LDR increase. During nighttime, the resistance will increase. So the difference in resistance is actually very high. The difference in resistance is very high. So, for example, during daytime, the resistance is very low, like less than 100 ohm. Okay, about 100 ohm. So, for example, during daytime, the resistance very low is about 100 ohm. And then during nighttime, the resistance will become very high until like 1 mega ohm, which is 1 million ohm. Yeah. So you see, this is 6 volt. If during daytime, this is 100 ohm. Okay, during daytime. So, for example, during daytime, okay, during daytime, so this is only about 100 ohm. So we can calculate how much voltage between the base and emitter. Okay, we can calculate the voltage. So how do we calculate the voltage? Okay, so you see the ratio. You see this voltage here and the voltage here. Let's say this is VR. This voltage plus this voltage equals 6 volt. Okay, VR plus V base emitter equals to 6 volt. Okay, and then this ratio, okay, the ratio between this and the total voltage, 6 volt, equal to the ratio between the resistance, okay, resistance here and the total resistance. So that means this resistance of LDR and this resistance R, okay, basically it means like this. This resistance of LDR over the total resistance. That means resistance of LDR plus the resistance here, that means the total resistance here, is equal to the ratio between the voltage of the base emitter or the voltage that the LDR get over the total voltage, which is okay, total voltage or in this case is 6 volt. So you see, resistance of LDR is only 100 volt. 100 volt. So resistance of LDR plus the total. Okay, so this is 100 plus 10,000. So equals to voltage between base emitter and the total is 6 volt. So the voltage of base emitter is equal to okay, so it will be equal to 0.059 volt. So you see this voltage is so small, obviously it is not enough to turn on the transistor, right? Not enough to turn on the transistor, so the bulb did not light up. No collector current, so the bulb is not up. Okay, now how about at night time? Okay, during night time, this resistance become very high. For example, 1 mega ohm. So let's calculate how much is the voltage. Okay, that means the voltage here is this voltage here is ER. Okay, and this total voltage V. So this resistance here, this is R, L, E, R. This is R. It's all same thing also. The ratio between the resistance R, L, E, R over the total voltage R, L, E, R plus R. goes to the voltage of the LDR, if V over the total voltage. Okay, so this one is 1 mega, 1 0 0 0 0 0. Okay, over. So this is 1 0 0 plus 10,000. Okay, goes to V over. Okay, so V goes to so you get 5.944. Okay, so you see the voltage here is 5.94 volt. Okay, 5.94 here. So this is obviously strong enough to turn on the transistor. Turn on the transistor, so current can flow. Collector current can flow, so the light will turn on. So you see, how is it that this transistor can function as automatic switch? See, at night time, automatic turn on. Daytime, automatic turn off. Because the change in the resistance of the LDR. Okay, that's here. Okay. Okay, so let's say you want to modify this this circuit so that the light will turn on during daytime. Okay, I don't know why. For example, okay, maybe you want the let's say you have shop or something. Okay, okay, okay. As long as let's say that you want something to automatically turn on during daytime. Okay, let's say fan. Okay, we want the light fan. During daytime, okay, it's on. Okay, daytime, then after daytime is on. So during daytime, I want the fan to turn on. During night time, it's also I turn off. I want the fan to automatically turn off. For example, like that. For example, okay, but okay, whatever the what that you want. So let's say that you want to turn on something during daytime, but turn off during night time. What you do is same circuit, but you change the position of the LDR and this resistor. And then this resistor you move down here. Okay, resistor you move down here. And this LDR goes in the top here. Okay, change space between the LDR and the resistor. Okay, let's see now. Change place. So when you change place, you see what happens. During daytime, this resistance will be low, right? When this resistance is low, that means this resistor will get most of the voltage. For example, here, you see during daytime, this one, the voltage, this VDD is only 0.059. If only 0.059, that means what happened to the rest? What happened to 5.95 volt? What happened to 5.95 volt? 5.95 volt will go to the 10 kilo ohm resistor. That means this DR will be 5.5 sorry, 5.95 volt. Understand? So now that same thing happen here lah. This one small, so that means this voltage here. That means this one you will get a bigger voltage. This one will get 5.59 volt. So 5.95 volt. So and turn on the transistor lah. So this whatever lah, you want to fan, you want to light, bring on here, or sprinkler automatically spray water or something. This will turn on. Okay, during daytime. And then at night time, it will be the opposite lah. At night time, the resistance here will be high. Okay. Okay, so during night time, this resistance will be high. So that means this voltage here is high. So this voltage here is low lah. So very small. So this one will be off. So this one cannot turn on lah. Okay, get the idea. Okay, very simple. Okay, once you understand that, you will find that it is actually very simple how it works. Okay, so during daytime, during nighttime, it's not on. Okay, terbalik lah, opposite. Okay, you see lah. Okay, any question? So this is how we can use the transistor as automatic switch. Okay. Okay, so next, continue. Okay, this one it says thermistor in a heat control switch. Just now is LDR, light dependent resistor in light control switch. This one is thermistor in heat control switch. So again, thermistor is also a variable resistor. That means the resistance change according to temperature. Thermistor is a resistor whose resistance changes with its surrounding temperature. The resistance is high under room temperature. That means low temperature. As the surrounding temperature increases, the resistance becomes low and voltage across the thermistor decreases. Based on the concept of potential divider, when the voltage across the thermistor decreases, the voltage across the resistor will increase. When the value of VR exceeds the minimum voltage across PE, the base current will flow and the transistor will be turned on. This situation will result in a high current flowing into the circuit causing the bulb to light up. So this circuit is suitable as a automatic switch in a temperature control system. Okay, so you see, this is very similar with the light control switch just now. Okay, very similar to the light control switch just now. So you see, this thermistor, okay, this thermistor also made from semiconductor. That is why the characteristic is the opposite of the normal conductor. Normal conductor, we know that the resistivity for normal conductor, the resistivity will increase when the temperature increase, right? So it makes the resistance increase when the temperature increase. But this semiconductor is the opposite. When the temperature increase, the resistivity of the semiconductor will increase. So that means the resistance will increase. You see that? Okay. So that is why the thermistor, the resistance will decrease when the temperature increase. Okay. So for example here, let's say during normal temperature. Okay. Okay. So what kind of, because okay, here it says that automatic switch is a temperature control system. So one of the most simple example is fire alarm. Okay, fire alarm. So let's say when no fire, no fire, no fire. So that means the temperature is low. So the resistance is high. So when the resistance of the thermistor is high, that means this 6 volt, most of the 6 volt will go to the thermistor. And the resistor here, the voltage here, this one the voltage here will be high, this one the voltage here will be low. Okay, so for your information, the changes in the resistance of thermistor is also very similar with the changes in resistance of the LDR. That means when the temperature is low, the resistance of the thermistor is very high, very high. And then when the temperature is high, then the resistance of the thermistor will increase until very low lah. So when the temperature is low, okay, room temperature, so the resistance of the thermistor will be very high. So most of the 6 volt will go to the thermistor. So the 10 kilo ohm only get a very small voltage. So this voltage is not high enough to turn on the transistor. So the transistor is off. So off, so the fire alarm is also off lah. No current. Okay, no current. However, when got fire, okay, when got fire, okay, when fire hot, so the temperature will go up, the resistance will go down, so the voltage that the thermistor get will become very low. So this 10 kilo ohm will get a high voltage. That means most of the signal will go to the 10 kilo ohm. So this high voltage is enough to turn on the transistor. So this transistor on, so for current, current will be able to flow, and then the alarm will turn on. Okay, the fire alarm will turn on. Okay, and so this is the example of application for the transistor as automatic switch. So by connecting different type of sensor to the transistor, you can use the transistor to do a lot of different things. Okay, automatically turn on this, automatically turn off that. Okay, and do things automatically. Okay, so this transistor is a very special electronic device because okay, one thing that we did not learn here is that the transistor, when connected certain way, the transistor can be used to do mathematical calculation. It can be used to act as a logic circuit. Okay, logic circuit. That means it can, when fulfill a certain condition is fulfilled, then it can automatically turn on a certain circuit or turn off a certain circuit, allow current to go, does not allow current to go like that, according to special condition. Okay, so this transistor is actually the basic building block for our computer, our calculator, our handphone, all the automatic machine that can automatically turn on or off. For example, let's say, for example, anything that's automatic, for example, like automatic vending machine, the automatic parking system. You press a button, when your car reach there, you press a button, the ticket will come out. You pull the ticket, then only the gate will open. Your car pass through already, the gate automatically close. All of this automatic control system is based on logic gate or logic circuit, and all of this logic circuit is only possible by using transistor. So transistor is a very, very important electronic component. Okay, when you use very creatively. Okay, this depends on the creativity of the user lah. So if the user, the person that use the transistor is very creative, they can use it they can do many things. Okay, okay, So you will learn all of that when you go to higher level lah. So until here, you only learn some very basic application of the transistor, as current amplifier, as automatic switch. Okay, so these are the two very simple and basic application of the transistor. Okay, so until here, any question? Anybody have any question? Okay, thank you very much. Okay, thank you very much for responding. Okay, so the chapter 5 finish here lah. Okay, chapter 5 finish here.